Alrighty, howdy folks. So let's look at chapter 12, section 4. This is about the cross product of vectors. I'm sure you have done cross products and dot products in a whole bunch of classes, right? So if this happens to be a repetition, please bear with me. Maybe there's a thing or two that you learn new, so pay attention, and I'll solve a few problems to solidify the concepts. Okay? Definition. Whoa. If A equals A1, A2, A3, and vector B is equal to B1, B2, B3, then the cross product of vector A and vector B is the vector quantity A cross B and is given by A cross B is equal to, right? That form of A2B3 minus A3B2 is the first component, the X component, and A3B1 minus A1B3 is the Y component. That somehow doesn't look all that familiar, right? I'm sure what you are more familiar with is the determinant way of presenting this, and we can actually do that. So if you actually evaluate this determinant, you will get this one. So it's not that somehow they had the determinant first and then came up with this. It's the other way around. Okay. Anyways, so A cross B, we find this using this particular determinant of a matrix, of this 3 by 3 matrix. In fact, there are some people who actually add I and J, another couple of columns, the fourth column being this exactly the same as the first column, and the fifth column being exactly the same as the second column. And that way, the whole idea is you don't have to worry about the signs, in the sense, is this going to be negative when you multiply by J or not, and things like that. Well, if you are used to that and you feel comfortable with that, please be my guest and use that. But I'll just use the standard approach. I don't think this is any difficult at all. And directly I'll go to a theorem. The vector A cross B is orthogonal to both A and B. What? Orthogonal. What's orthogonal? Sort of perpendicular. Okay. So when you figure out this vector A cross B, that's going to be perpendicular to both A and B. And you really have to be cognizant of this fact, because pretty soon we are going to deal with lines and planes, equations of planes, and stuff like that. And it becomes important to know that A cross B is orthogonal to both A and B. Okay. I think I mentioned this, right? Suppose you have a plane. There is what is called a normal vector to the plane. That means there's a vector that is sticking perpendicular to that plane. Can you imagine that? Like if you imagine your table is a flat table, is horizontal flat table, and uh, you can clearly see a vertical line sticking out of the table, which would be perpendicular to this plane, and that that is called, that line, that perpendicular line to the plane is called the normal to the plane. Okay, so pretty soon when we deal with vectors, when we deal with planes, we may use this concept of A cross B. Suppose somebody says, hey, find a normal vector to this plane. We'll say, just give me a second. Let me figure two vectors on this plane, vector A and vector B, which I will tell you how to do. And then you say, I'm going to figure out A cross B, and that's going to be your normal vector. See, that's how we actually make use of this concept that A cross B is orthogonal to both A and B. Okay, that's coming up, but just wanted to give you a bit of a heads up on that one. Okay, all right. What else? To find the direction of A cross B, we apply the right-hand rule. I believe I talked about how to do the right-hand rule, and in fact, I'm going to solve a problem, and that's when I will actually discuss specifically how to figure this out. It would be a repetition, but I don't mind repeating that aspect of it, just in case there's someone who doesn't seem to understand that clearly. Okay, all right. Next theorem. If theta is between 0 and pi, 0 and pi included, is the angle between the vectors a and b, then the absolute value of a cross b is the absolute value of a times absolute value of b times sine theta. Okay, notice something here. This one says the magnitude of a cross b is the one which is absolute value of magnitude of a times magnitude of b times sine theta, right? That only gives the magnitude. But what about the direction? Well, like the previous statement says, you have to find the direction of a cross b by applying the right hand rule. That means you figure out a crossed b, something that is perpendicular to both a and b. Okay, you got to do it that way. I'll solve a few problems, but just keep in mind that this merely gives you absolute value of a times a magnitude of a times magnitude of b times sine theta. This gives you the magnitude. Okay, I think that's the point I'm making here. With this, while this gives the magnitude of the cross product, to find its direction, we use the above mentioned right hand rule. Cool. Corollary. Uh, what's a corollary? Corollary uh, is like something that you can derive from the theorem. If the theorem says something, notice just from the theorem we can deduce this other fact. That's the whole idea. And two non-zero vectors a and b are parallel if and only if a cross b is equal to 0. What? Two non-zero vectors a and b are parallel if and only if. Did I mention about what this phrase if and only if is? Well, that's a pretty important phrase in mathematics, and it doesn't have the same meaning as regular day-to-day English meaning. Okay, if and only if P if and only if Q means if P is true, then Q is true. And also if Q is true, then P is true. Okay, if P then Q and if Q then P are both true if we say something P if and only if Q. So how do we apply that here? Because we have a statement called two non-zero vectors a and b are parallel before if and only if, that's the P part, and the Q part is a cross b is equal to 0. So we say this means if two non-zero vectors a and b are parallel, then a cross b is 0. At the same time, if a cross b is 0, then the two non-zero vectors a and b are parallel. Okay, that's the implication of this. And that apparently is the corollary from the theorem, meaning that is something that you can figure out from the previous theorem. Is that true? Let's see. Vector A and vector B are parallel. In that case, what happens to the angle between vector A and vector B? If two vectors are parallel to each other, what can you say about the angle between them? The angle should be 0. Is that the only way? Is that the only angle? Would two vectors be parallel? Would two vectors being parallel mean only that the angle between them is 0? Careful. The truth is, the angle could be 180 degrees also, or pi radian also. Even then, of course, their directions would be opposite to one another in that case, but they could still be parallel to one another. Well, regardless of the angle being 0 or 180 degrees or pi radian, sine theta would be sine 0 or sine pi. They are both 0. So obviously the magnitude based on this theorem would be by virtue of sine theta being equal to 0. This whole thing, A and B are not 0. They are non-zero vectors. So magnitude of A times magnitude of B is some non-zero quantity times 0. So that's going to be 0. So the magnitude of A cross B is going to be 0, right? If the magnitude of A cross B is 0, then automatically that is the 0 vector. So to be more precise, I should have said A cross B is 0 vector. But in the context, people understand that when, oh, by the way, did they ever mention this? Oh, okay. A cross B, yeah, okay. Whew, scared me. Then the cross product of A and B is the vector quantity. So the cross product actually ends up being the vector quantity, unlike the dot product. The dot product of two vectors is a scalar, but the cross product is still a vector. Cool. Okay, so where are we? Okay, so I demonstrated that if A and B are parallel, vectors A and B are parallel, then theta is 0 or 180, and so the magnitude of A cross B would be 0. So clearly this is true. If this is true, that is true. At the same time, if A cross B is equal to 0, that means this is a 0 vector, then the magnitude is 0. So that means if you go to this equation, this left hand side is 0. So 0 equals magnitude of A times magnitude of B times the sine theta. Would you agree? If A cross B is equal to 0 vector, then the magnitude of that A cross B vector must be 0, making the left-hand side 0. So we have magnitude of A times magnitude of B times sine theta is equal to 0. Okay, what does that mean? That means either A is 0, magnitude of A is 0, or magnitude of B is 0, or sine theta is 0. But we already said that non-zero vectors A and B. So magnitude of A is not equal to 0, magnitude of B is not equal to 0. So the only thing that must have happened is sine theta must have been 0, right? Sine theta is equal to 0 means theta has to be either 0 or pi. We don't need to worry about the 2 pi and the 3 pi and all the multiples of pi. Okay, so we'll just pick those, and in both cases where theta is 0 and theta equals pi, the two vectors are parallel. So notice if the cross product is equal to 0, then the vectors are parallel, right? That's the proof. That's something that you can derive based on the theorem. That's why it's a corollary. Cool. Next, the magnitude of A cross B is equal to the area of the parallelogram determined by vectors A and B. So there's another practical use of A cross B. Suppose we have vectors A and B. I happen to place them so that their tails touch each other. Suppose we have two vectors like this. Can we create a parallelogram with these two as sides? Yeah. Draw a line at the tip of A, at the head of A, draw a line parallel to vector B, and at the tip of B, draw a line parallel to vector A, and they intersect at a certain point, and we have a parallelogram. So the claim here is that the area of this parallelogram would be whatever the magnitude of A cross B is. Ain't that interesting? Okay, so let's see. Why is that true? That is true because, as you can see, if the angle between these two vectors A and B is theta, this height is h. I'm claiming that is actually magnitude of A times sine theta. Is that true? Would you agree with that? Well, let's say I had scooted this line, this vertical line, or rather it is perpendicular to this vector B, making this a 90-degree angle. If I had scooted this over here so that this forms a right triangle, in that case, would you agree sine theta would be h over magnitude of A, opposite over hypotenuse? Sine theta is h over magnitude of A. Therefore, h itself, multiply both sides by sine theta, by A rather, h over absolute value of A, right? H over magnitude of A. So h equals magnitude of A times sine theta. Why do we need this h? Well, recall the formula for the area of a parallelogram. Base times height. How do you measure the height? By drawing a perpendicular. To this base one, you draw a perpendicular, and that's how you measure that height. So we have the base. What's the length of the base? Base is this vector B. But we're talking about the length of that vector. When we say base, we are talking about the length, the magnitude of that base. So base magnitude would be absolute value of B, that is magnitude of B, times this height. So let me show you that. Come on. I don't know. It looks okay on mine. All right. So area of the parallelogram is h times the magnitude of B. But h we already said is magnitude of A times the sine theta. So here we get this. And isn't this by definition here magnitude of A cross B? That's the idea. Cool? All right. I'm going to insult your intelligence. Look at this stupid problem. Find the cross product and verify it's orthogonal to both A and B. Oh, okay. At least that part is okay. They're not simply asking us to find A cross B, but also verify that it's orthogonal to both A and B. A cross B itself, you make this determinant, right? IJK, A1, A2, A3, B1, B2, B3. And in this case, A1, A2, A3 are 4, 3, and negative 2. B1, B2, B3 are 2, negative 1, 1. So plug. Okay, for the benefit of those who may have forgotten about how to do this 3 by 3 determinant, what's the idea? You first take this I. You can expand about anything, and in this case, let's expand about the first row. This has 3 rows: first row, second row, third row, and 3 columns. First column I4 2, second column J3 1, negative 1, third column this, right? And I said we'll expand about the first row. What does that mean? We'll say I times that vector times something. What is that something? Somehow I like to call it as a submatrix. I don't know if that is mathematically the right thing or not. The submatrix I'm talking about is obtained by doing this. We pick this element I, right? Where is it? It's in the first row and first column. So do one thing. Erase, sort of strike out this first row and the first column mentally. Don't actually scratch it off. but mentally think of this as this column and this row have been crossed out. So when you do that, all you're left with is this, and this 2 by 2 matrix. That submatrix is what you multiply I by, the determinant of that matrix rather, like this. Cool? I times this submatrix. How did we get the submatrix? By crossing out that way, the row in which that I is and the column in which that I is, and looking at whatever is left over. Cool. And then what? We said we are going to expand about the first row. So we pick this element, J, right? And so J times, again, submatrix, the determinant of a submatrix. How do we get that? Cross out this row, this column and this row. That, would you agree, leaves us with 4, 2 vertically, and this -2 and 1, this is gone. 3 and -1 are gone. So we are left with 4, 2 vertically, -2, 1 vertically under K, the ones under K. There's one more point I need to mention. Just like I said, J times 4, 2, -2, 1. But what's with this negative sign, man? Well, here is the idea. Should we use a positive or a negative sign as we do this? That depends on which row and column is this element. We decided to use element J. Which row is it in? First row. Which column is it in? Second column. So first row, second column. So you take -1 raised to the row plus column. -1 raised to, the row happens to be 1 and the column happens to be 2. -1 raised to 1 plus 2 is -1 raised to 3. -1 cube is negative, and that's why this guy is negative. Okay, now what about I? Okay, first row, first column. So that means -1 raised to 1 plus 1. 1 plus 1 is 2. So -1 raised to power of 2, or -1 the quantity squared, which is +1. And that's why this ended up being positive I times. Okay. Now let's move to the K, the final one. First, let's figure out the sign. K, which row and column? First row, third column. So -1 raised to 1 plus 3. 1 plus 3 is 4. -1 to the power of 4 is clearly positive. 4 is an even number, so -1 raised to an even number is +1. So we have positive K times which submatrix? Erase the first row and first column. We are left with the submatrix. That's what we do, right? And excuse me, sorry about that. How do we figure out the determinant with 2 by 2 matrix? Multiply these two, 3 times 1 minus -1 times -2. So 3 times 1 is 3 minus -1 times -2 becomes just -2. 3 minus 2 is 1. So 1 times I. Got that. 4 times 1 is 4 minus 2 times -2 becomes 4 plus 4 is 8, but we have a minus here, so minus 8J. 4 times -1 is -4, minus 6 is -10, and that's why this is -10K, right? I'm sure you already knew that. Cool. Now about this verifying that this is orthogonal to both A and B. A bit of a challenge. How do you determine if two vectors are orthogonal? It's something that we learned in the previous section, right? If two vectors are orthogonal, then their dot product is going to be 0. That's it. So that's the concept we are going to use. We know the A cross B vector, and we'll take a dot product with A, see whether or not that is 0. If it is, then the A cross B is definitely orthogonal to A. Similarly, we'll take A cross B and take the dot product with this B and see whether that is equal to 0. If it is, A cross B is orthogonal to B. Okay? A cross B dot A. A cross B, well, it's in terms of ijk, but I can clearly write that in the using this angle bracket notation. 1, -8, -10, and A is already given to be 4, 3, -2. What do we do to find the dot product? Like components, multiply x component with this x component, 1 times 4, plus -8 times +3 is -24, plus -10 times -2 is going to be plus +20, and so that turns out to be 0. Similarly, A cross B dotted with B is this, and that's 0. So the vector A cross B is in fact perpendicular or orthogonal to A and B both. Cool. All right. Cross product of standard basis vectors. This ijk. Right? What's the cross product of those vectors? What is I cross j? What's j cross k? Things like that we need to know. For that, it's a good idea to make up this figure with these arrows like that. Okay, you draw ijk like in a triangle and draw kind of circular arcs. And the idea here being, if we go this way, we start at I, and the arrow is indicating that we need to go this way. Rather, we'll put it this way. If we go in the direction of the arrow, that means we are going in the positive direction. And so I cross j in that case would be this one, which is positive k. Cool. We are not going against the grain. We are going along with the grain. So I cross j equals k. Now, what about j cross k? Do the same thing. Start with j. J, we are going along the grain. Cross k, therefore should be equal to just I. What else is left? K cross I. Yep, k along the grain, cross I must be j. Cool? That's the first stuff that I wrote. I cross j is k, j cross k is I, k cross I is equal to j. Now, what about, what was the first one I did? I cross k. Okay. Now we are going against the grain, right? I cross with k. Oh, okay. Will be j, but the only thing is, because we went against the grain, we have to say negative j. I cross k is negative j. Similarly, k cross j, negative I. J cross I against the grain, negative k. That's the idea. Cool. This will come in quite handy. And then, properties of cross products. Anytime people talk about properties, you got to pay attention. Some of them are going to be fairly obvious. Oh, come on, man. Duh. But some not necessarily so obvious. If A, B, C are vectors in V3, some vector space of 3 dimensions, maybe we could say R3, that funny looking R for real number, R3, and you write 3 is not as a subscript but as a superscript. R3, that means real number, 3-dimensional real numbers, both all x, y, and z real number axes. And C is a scalar. Then this is what happens. A cross A is equal to 0. What? A cross A is equal to 0. Why? But wait a minute. Isn't the magnitude of A cross B equal to magnitude A times magnitude B times sine theta? Yeah. If we're talking about A cross A, what is the angle between A and A itself? Got to be 0. So the magnitude of A cross B, based on that, you get 0. Well, if magnitude is 0, then the vector is 0 vector. So, well, here I did put that, called it 0 vector. But like I said, some people don't do that. They just say, well, it's obvious that you're talking about A cross A, its result must be a vector. So when I say 0, I actually mean 0 vector. Okay. Next property. A cross B is negative B cross A. Where do we get that from? Check this out. Do a right-hand rule to figure out the direction. It's for one simple reason, and the reason is the direction of that vector is going, of the two vectors is going to be opposite to one another. Why is A cross B the negative of B cross A? That is because, like I said, the direction of those vectors is going to be exactly the opposite. How? Can you figure out, take two vectors, imagine two vectors, and do a right-hand rule, draw two vectors A and B, do a right-hand rule and figure out A cross B. Well, you stick your fingers towards A and curl your fingers towards B, and you get a vector that way. But if you do B cross A, you will have to flip your palm and do B cross A, and it would have the exact opposite magnitude. Opposite direction. See, that's the idea. And also, here we do have some examples. I cross J is equal to K. What is J cross I? Check this out. J cross I is negative K. I cross J is K, but J cross I is negative K. Or we can go here. I cross J is positive K, J cross I against the grain, so negative K. Right? Here is another situation where we're seeing that. Similarly, J cross K is positive I along the grain, whereas K cross J is against the grain, we get negative I. That's another way to look at it. Okay. Okay, let's move on. Distributive property applies. A cross B plus C is A cross B plus A cross C. Okay. A plus B cross C, again, somewhat straightforward, intuitively obvious. A cross C is A plus B cross C. And A dot B cross C is A cross B dot C. Now, you tell me, that doesn't seem so obvious. At least you must be a genius if that is obvious to you. For me, when I first saw it, I was like, what? How do you get that, man? And so it turns out A dot B cross C is the same as A cross B dot C. All right. And finally, this last one, A cross the quantity B cross C is totally weird. The vector triple product A cross the quantity B cross C is A dot C times B, regular times. What? I thought vectors you have to say, if you're multiplying two vectors, then you got to say either dot or cross, man. Uh, but wait a minute. I don't think I ever mentioned it. Is there such thing as vector A times vector B? Just simply times B? Not at least at your stage. When you get to tensors, there is something like that. But at your level, at this level, uh, vector A times vector B doesn't make any sense. The times has to be one of the products, either a dot product or a cross product at your stage. Okay, so what's up with this guy? Vector A dotted with vector C, and then times, just a regular times B? Didn't we violate what I said? No, we didn't. Recall. Maybe I'll put it this way. Can I multiply a vector by a scalar? Is that okay? Just regular multiply? Yeah, that is okay. Taking a vector and multiplying it by a scalar, that's okay. Well, isn't A dot C just a scalar? Yeah. So all I'm doing is multiplying this B by a scalar called A dot C. That's totally cool. No violation occurred. Similarly, A dot B here is a scalar and I'm multiplying by C. So A cross B cross C is equal to A dot C times B minus A dot B times C. Now, there's an obvious question that you might have. How the hell do I know you are right, man? You may just be throwing that out. How do I believe you? Right? So the truth is, I have to prove all these things to you. Maybe I'll do this. This is what I figured I'll do. I'll prove 5. All these other ones are stupid. They are fairly straightforward. Uh, you try to prove to yourself the 6 by following a procedure similar to what I'm going to show you for 5. Okay? So let's prove 5. A dot B cross C is equal to A cross B dot C. So the standard strategy is to say, let A equal A1, A2, A3, B equal B1, B2, B3, and then you pick up the left-hand side and figure out what the left-hand side is. Then pick up the right-hand side and figure out what the right-hand side is. If they both happen to be the same, you're done, right? I don't know if any of you is a math major, but when you actually take serious math courses, the ones that involve proofs, problems like this, proofs like this is a luxury. It won't be like this at all. Things that proofs are so much more complicated. All right, so as promised, I picked the left-hand side, A dotted with B cross C, and A is A1, A2, A3. B cross C, instead of doing the determinant and all that, I just used this version of it. Where do you get this from, man? Well, use the determinant, man, and you will find that this is what this turns out to be. So now, what's the dot product of this? Well, take the first component and multiply by the first component of the second vector plus second component of the first vector times second component of the second vector plus the third component of the first vector times the third component of the second vector, right? That's how we find the dot product. And when you do that, I'll just say, trust me, when you do that, this is what you get. Now, let's pick up A cross B times dotted with C. And for A cross B, we will write this way. And C is C1, C2, C3. Again, the dot product. When you multiply, you get this. And these two are exactly the same. What? I don't see that, man. Okay. Let's pick one component here, the first component, and see if we observe that component here. By the way, there are 6 terms here and 6 terms here as well. Good, that's good. A1, B2, C3. Is there a plus A1, B2, C3? Ta-da! A1, B2, C3. Minus A1, B3, C2. Is there a minus A1, B3, C2? Ta-da! A2, B3, C1. A2, B3, C1. Minus A2, B1, C3. Minus A2, B1, C3. So on. So check for yourself. That's it. They are actually equal. So this is the way you can prove. Now, yeah, that other one, that 6, is a bit tedious, but you can do it, right? Cool. Theorem. The magnitude of the scalar triple product. This is called the scalar triple product. A dot B cross C, which is what we just talked about, is equal to the volume of the parallel pipe determined by A, B, and C. Parallel piped? What the heck is that? This one. So if you have one side of this parallel pipe is A, and a second side is B, and the third side is vector C, okay? Then if you figure out A dot B cross C, A dot B cross C, and A dot at that, A dot with dot, take the dot product of A with the cross product of B and C, you get the volume of this one, right? Wait, this property says we could instead take A cross B and then dot it with C. Could we do that? Yeah, you can, right? Either way, you compute the volume, you'll get the same thing. It has to be true. Keep that in mind. All right. Now I'm going to solve a few problems and solidify the concepts. Find a vector, not with determinants, but by using properties of cross products. Okay. Like what? What's I cross j dot cross with k? This one is saying, okay, now don't do ij and all that. The determinant, just figure out by properties. Okay, I cross j. To me, anytime I have this, I just go to that figure. Okay, let's recall that. I cross j to along the grain k. So that's k cross k, right? What is k cross k? Same vector, so that must be the 0 vector. As simple as that. 2. K cross I minus 2j. Well, can we apply the distributive property? K cross I minus K cross 2j? Yep. So this is K cross I minus 2 times K cross j. K cross I. K cross with I along the grain, so must get positive j. K cross j against the grain, so you should get negative I. K cross I is J. K cross I is J minus K cross J is negative I. So minus 2 times negative I. And this is 2I plus J. Cool? All right. 3. J minus K cross K minus I. Well, distributive property. J cross K minus J cross I minus K cross K plus K cross I. It's all this distributive property is just like if this were to be A minus B times C minus D, what would you do? It's kind of like that. There's nothing big deal about this. This is more or less a straightforward property. Okay, J cross K is I, J cross I is negative K, K cross K is 0, K cross I is J. Ain't that right? So this is going to be I plus J plus K. Did I sound southern enough for you? All right. So silly problems like that. Find magnitude of U cross V and determine whether U cross V is directed into the page slash screen or out of the page screen. This is the one where I said, all right, boys and girls, I'm going to show you a little bit of how this direction thing works using right hand rule. You kind of stick your fingers so that all your fingers are pointing except the thumb. The 4 fingers are pointing towards you. Well, you can orient your palm in infinite ways, but in one particular orientation, you can curl your fingers so that they can be curled towards that V. Would you agree? When you do that, your palm would actually be facing up, would be slanting down, but the palm itself as such would be sort of facing up. Well, and as you curl your fingers, notice your thumb would in fact be sticking out of the screen or page. You agree? That's the idea. And magnitude of U cross V is magnitude of U times magnitude of V times sine theta. Theta is 45 degrees and sine 45 square root of 2 over 2. So 20 times square root of 2 over 2 sticks. To find the direction, stick your right hand such that the fingers are pointing towards positive U. Orient the palm so that the fingers can be curled towards positive V. When that is done, your thumb points out of the page slash screen. Thus, U cross V is directed out of the page screen. All right, next. Find the area of the parallelogram with these as vertices. Parallelogram. So, wait. Let me pause here. All right, I'm back. Sorry for the pause. Okay, so what's the idea? The idea is we have vertices of P, Q, or S. You remember typically when we label things, we label them in a order. P, Q, and from Q we go to the next vertex, R and S, like that. So what am I talking about? Why don't I just write it, man? Yeah, basically, come on. 10. Okay. Hmm, interesting. If I do that, erase marks. Come on. Okay. So I need to push backward. All right. A parallel. Boy, close enough for government work. P, Q, R, S. That's how we label, right? That's all I wanted to show. Okay. So which ones are adjacent? PQ and PS. So we saw that if we had vectors A and B like this, let's say that's vector A and vector B, and the area of that is simply the magnitude of A cross B. So it turns out that one of them is we just need to do PQ cross PS. I'm calling it B and A. I don't need to. Just say PQ crossed with PS. But the question is, do we know if we are given points P and Q, how to find the vector PQ? Simple. Head minus tail. Remember that. PQ is head minus tail. Head happens to be the Q here. PQ. Q is the head, P is the tail. Because the vector starts at P and ends at Q, right? And so because it ends at Q, Q happens to be the head and P is the tail. 3 minus 1, right? Head minus tail. 3 minus 1, comma 3 minus 0, comma 3 minus 2. And that's what I wrote, 2, 3, 1. Similarly, PS would be PS 5 minus 1, comma 2 minus 0, oops, comma 7 minus 2. So that's 4, 2, 5. So compute the cross product. Straightforward IJK stuff. I times the submatrix, blah, blah. 5 times 3 is 15. 15 minus 2, that's what I wrote. Minus J times 2 times 5 minus 4 times 1. Plus K times 2 times 2 minus 4 times 3. Ta-da! And we do not get the magnitude. We actually got the cross product vector PQ, but we just need to find the magnitude of this vector. How do we find the magnitude, folks? Yeah, just the square root of 13 square plus negative 6 the quantity square plus the quantity negative 8 square. You do that, and that turns out to be square root of 269. Right? That's it. That's how you find the area of the parallelogram. Now find the volume of the parallel pipe with adjacent edges PQ, PR, PS. Now they are actually telling us which edges are adjacent, okay, given PQRS. So this time I was wise enough to construct a figure for you so you can see. I should have had that sense even for the previous problem. If only I drew a similar picture like this. Instead of doing a sloppy job by hand, things would have been so much fine. Sorry about that, folks. You do not deserve that kind of torture from me. But what can I do? Please forgive me. PQRS. Oh, what's that? There was something about PQ cross PR dotted with PS, right? A cross B dotted with S, or A dot B cross C, all those things. Yep, that's where we get. We'll find the magnitude. So I'm saying PQ dotted with PR cross PS. PQ dotted with PR cross PS. If you want, you could do PS dotted with PQ cross PR. Maybe you might want to check that. Again, PQ, figure it out, head minus tail, PR, head minus tail, PS, head minus tail, PR cross PS, that's this vector. and the PQ dotted with that, right? So the dot product, negative 4 times 9 plus 2 times 4 plus 4 times 11, all that stuff, that turns out to be 16. So 16 cubic units would be the volume of this parallel pipe. Who cares? No, we all care. We all should care. Uh, this is because when you do fluid flow, chemi guys do, civil guys are interested, mechanical guys are interested, electrical guys don't give a damn. Um, Computer science, yeah, not at all. That's why I don't think computer science people even take Calc 3, right? Figuring out volumes of parallel pipes becomes necessary because when you're talking about fluid flow, your what is called control volume may in fact be a parallel pipe. So you're trying to see how much volume, what's the volume of this fluid inside this parallel pipe at time t1, and then find volume at t2, things like that. So you need these concepts. They have some practical significance. All right, folks, that's it.